Hello, in this video I will tell you about quadratic sorting algorithms. There are different sorting algorithms, it's a larger topic. So this is about some simpler ones that are, I hope, easier to understand and to implement if you need to implement sorting yourself, although many languages, of course, do indeed allow you to sort data by their built-in algorithms. But still, I think, well, not only I think, but many lecturers think that understanding simple sorting algorithms with different approaches is a good thing to start. It is a good way to start understanding overall topic of sorting. And overall topic of sorting is quite important. I can try to prove it to you because there is a set of books by Donald Knuth, quite famous set of books among programmers. I think, yeah, so here are some of the three of them. And the third volume, it's called Sorting and Search. So among the three first books by Donald Knuth, one of the three books was called Sorting and Search. So sorting is like half of 1/3 of his work. So indeed, sorting algorithms is quite an important topic, and we are starting with the most easy to understand sorting algorithms, and the word quadratic will refer to the working time. So we will be learning algorithms that are rather slow by the sorting standards. So in another lecture you will learn faster sorting algorithms, but today, okay, they are slow, but for very small, for not very huge arrays, for not very huge sets of data, even they can be applied. And also they're nice because their ideas can be reused in many ways. So for example, well, probably I will have time to show you the correlation between, well, the similarity of the approach of sorting and some other tasks that can be done in a similar fashion. So I will be sorting some data on the whiteboard, and of course it's not important what data do I sort. I can you can sort strings alphabetically or letters by the order in the alphabet, but the usual example will be to sort numbers, integers. But of course these algorithms can be applied to any type that have comparisons. So if your data has elements of the same type, and these elements can be compared by smaller or by the operator smaller, larger, and equals, then you can apply, and this comparison is working and consistent, then you can apply these algorithms. Okay, so let's draw some unsorted array like 2, 3, 9, 5, 6, 6, and it's normal that some of the elements are equal. Of course, we want our algorithms to work as well if the array has equal elements inside it. And I will be, usually when people say sort, they mean sort in increasing, or rather say non-decreasing order, because in the end there will be 6 and 6 together in the same place, so it's formally not correct to say that it's increasing order in the end. We say it's non-decreasing, so there is increases or equal levels, and it goes generally like this. So we will sort this in it's actually quite my example is rather almost sorted. There is a way to formalize that it is like almost sorted, but anyways, our algorithm of course should work with both randomly shuffled and almost sorted sets of data without problems. Okay, so what can we do with this data? One thing that we can try to do is to find at least some element that that is obvious for us where it should go. So you see over here that 9 is placed in a very wrong place. So let's think about the 9. It is the maximum of these of the elements, and why is it not located in the correct position? So let's start with the algorithm called selection sort. So yeah, many algorithms will have the name something sort. So like it's a noun, yeah, something sort. It's formally like selection sorting algorithm, I think, but selection sort is the way call it, and we will select the value that will fit finally into, or that we know in which position it fits. Of course, so I am telling right now the algorithm that should be formally called maximum selection sort. I am looking for a maximum and doing something. But of course, absolutely symmetrically, you can think of create the minimum selection sort that searches for the minimum and does symmetrical things. So let's do the maximum selection sort. I find the maximum, and it's not finding the maximum, it's finding the index of this maximum. So I make a for loop, but I want to save not the fact that 9 is the largest element, but the fact that its index, I think we are speaking about zero-based indexing, so its index 2 is the index of the maximum element. My for loop ends up with the information that in the index 2 there is this huge element, the hugest element. And what do I want to do? So let's speak about where do we store the result. There are two ways to do sorting. One way is to receive another array, another Python list or vector or array list, anything, another structure with the same data but sorted. So in this case, definitely the programmer shouldn't change the original array. So if you want to not change it but to receive the result, it's sorting into some other positions, some other linear data structure. But sometimes you want to do it in place, they say in English. So sorting in place, which means that we are allowed and actually we are expected to change this array. So we don't care about the previous order. There is no important information for us about this order, so we can lose this information and rather have the array sorted inside this area of memory. So no new memory is created. Right here, let's sort it. And let's in this topic in quadratic sorts, let's rather usually do in place sorting. So we don't want to spend some space for the copy of the array. We just have this amount of space, and inside this space we will sort. So finally, if we are doing it in the same array, 9 wants to go into this position. But quite obviously, if we just assign this cell with a 9, then we lose this information. This 6, well, there is another 6, but if it was to be a unique number, then its value would be just forgotten, and we lose some information. That's definitely a stupid thing to do. So we want to put this 6 somewhere. Where do we put it? Well, you can make a special variable or something, like a special list for extra elements, but this 9 in the position 2 will move right to its good position. So it would be also stupid to leave a 9 over here. If we put a 9 here and a 9 is stored here as well, it looks like our array has 2 9s, which is not true. So we should put something here, and we should put 6 somewhere. Well, so the good solution comes quite easily. Let's swap them. Let's interchange their positions. So 6 goes here, and a 9 goes here. All right. After this for loop, we found the index of maximum and swapped it with the last element. Note that it is very normal that the maximum element will be already on the last place. So possibly your swap in the end, after this for loop, you swap index 5 with index 5. It's okay, you spend like 3 operations for swapping these two elements, but who cares? The if, you don't need to write an if like don't do the swap if it's already the good index, because this if operation will take extra time in large arrays for in many cases. So in many cases this if will add an extra check, and in a few cases this if will save you from swapping the same element. Why do this? Generally you don't need to do this. So we swapped some position with the last position. Probably these two are the same. And we received the maximum in the ideal place and some elements yet to be sorted in the first 5 positions in this case. So in the first n-1 positions. This is wonderful and this is yet to be done. Well, we have some smaller array to be sorted. Probably, if you like recursion, you can even implement this recursively or say algorithmically that we are right now we do the same for this part and so on, or just organize it inside outer for loop. So the outer for loop will say, okay, do it for this part of the array. A prefix, the good word is prefix. Then do it for this prefix of the array. Well, let's actually do it. So we search for the index of maximum, and for now it is not important which 6 I select. We'll talk about equal elements later at some point, but now let's say that our simple maximum search says that index 2 has the maximum. It's the largest number that we have seen. So we remember this index 2 as the maximum, and we do swap. Why not? So it looks maybe inefficient and stupid, but it's okay. Your maximum found this, your for loop found this position of maximum. You swap it with the last element. So you swap a 6 and a 6 wonderfully. And that's it. You put 6 into ideal position and you continue with this prefix of the array. Yeah, so our next iteration, our second for loop, put the 6 in the ideal position. And you do that for prefix of length 4, of length 3, and so on. Where do you stop? Well, some programmers, there are like 2 options where to stop. You can definitely want to do it for the prefix of length 2, because it's possible. And it's a good exercise to understand when it happens. An extra exercise, think about when, what example of the initial data it should be, so that this sort, this part, the iteration of on the prefix of length 2 is needed indeed. So think of some example. Of course, you cannot leave out this part. The prefix of the length 2 should be processed. Find the maximum, you swap it so that it comes to position 1, then you go to situation of you need to sort the prefix of length 1, and then you can either do this, because I hope that your for loop will work in this case indeed. It's a good check for yourself. When you write the actual code in programming language, just make sure that your code is not like degenerate, not working with special cases correctly. It's a good code style. Check that your code indeed would work for this prefix. It would find the maximum in position 0, swap position 0 with position 0, and say I'm okay. So you can either run this procedure for loop for length 1, or you can say that for length 1 this sub-array, this prefix, is already sorted, so let's not spend time at all. So you can just leave out this size and not do anything on the prefix of length 1. So for prefixes n minus of length n minus 1 and so on, and length 2 and probably length 1, but why? You do the maximum search and the swap. This is called selection sort, and let's understand the working time of this algorithm. So the first for loop uses it's a linear search over the array for finding the maximum element, or better to say the index of the maximum element, not the value but the index. So it took like linear time n operations to find this element. And okay, and there is also like 1 operation or 3 operations of swapping. So it's in the asymptotic notation, it's not important whether it's 1 operation or 3 operations. So it's asymptotically about 1 operation of swapping the elements. I'll write it down in the right part. It's easier for us to do it like this. Then for the next loop of length, prefix of length n minus 1, you do n minus 1 operations for loop and finding the maximum value, and one swap operation. Then the next loop is n minus 2 operations for loop and the swap, and so on. And for example, you even even allow us to do the stupid for loop for the length 1. So there will be a for loop of length 1, and the swapping operation, the definitely stupid swapping operation for the length 1. So this is the number of operations we do in the selection sort. And this is the sum of arithmetic progression, which is n times n plus 1 over 2. And this is n swaps that we do in our algorithm. So the working time is like this. And I can expand, so it's n squared over 2 plus n over 2 plus n. And then mathematicians say, okay, asymptotically, like when n grows, these terms are negligibly small comparing to this term. And in this term, we don't really care about division by 2, because it's like here we didn't care whether it's 1 operation or 3 operations for swapping, and here we don't care about divide or 2 or don't divide or it doesn't divide by 2. So the growth of this formula is quadratic when n grows. These terms don't really matter. This dividing by 2 doesn't really matter. So the working time is O large of n squared. The asymptotics of this time is growth quadratically as n grows. And that is finally, I didn't say it in the beginning, why this adjective is used over here. The quadratic sorts is the sorts that use n square, asymptotically n square time for working. Not very fast, so you don't sort like an array of size million with this algorithm, but an array of size 10 or 100, why not? N squared operations, around n squared operations. Well, generally, even like if you want to remember this constant, then it's like n squared over 2 operations. But then you have to define what a primitive operation is. So n squared operations, not very fast, but quite reasonable and quite easy to code. So, and the idea, once again, is to find a good element and put it into the fitting place, into the perfect place where we can definitely put it. All right, so this was our first quadratic sort. And the next, well, actually, maybe let's even do from this position. Let's do the sorting from this very position. So, the name of the next sort will be insertion sort. Insertion sort. And it's also a good approach to the data that you have that I want you to remember, and I hope I will have time to show you how very other task can be solved by the similar fashion. So the fashion that I'm speaking here about here is the following. Let's also previously we did put some elements to the good positions, and now let's have growing the part of the array that already has the order of the elements wonderful and perfect. So and the part will be in from the beginning. So once again, the word prefix means the beginning of your any array, and we will increase the size of the prefix in which the order of the elements is already perfect. And I can show you some such size to begin with. It's quite optimistic. It's not 0, but if you think formally, the prefix of size 0 is sorted indeed. But fortunately for us, even the prefix of size 1 is already sorted. I can be sure that if you consider only this subarray, this prefix, the sorting is already done on length 1. And so it's maybe for those who know, it's like mathematical induction. You start with a base and then you go to the larger and larger values of n, which is not important if you didn't understand this phrase. So we already have something correct over here, and we will continually increase the incrementally make this prefix of wonderful order larger and larger until we sort the entire algorithm. So let's think about adding a, this is already wonderful, let's think about adding a 3 into this perfectly sorted prefix. Well, 3 is located correctly relative to the already sorted elements, so we can simply say, okay, this is also already sorted. If you see the element, it will not be a separate if statement, but it's just a simple case to start. If the next element is larger than the largest of the elements in this part, like 6 once again, then you don't need to do anything. You just say, okay, my ordered subspace is becomes 1 unit larger. So I had everything correct in the prefix of length 2. Now I also freely I have everything correct in the prefix of length 3. And now finally comes some serious work, because 5 doesn't fit perfectly into this prefix part, in already sorted prefix part. So what do we do with the 5? But after we say that the prefix of length 4 is wonderfully sorted, these elements will be sorted non-decreasingly. So these 5 have to fit somewhere into its desired position. And all the elements of this prefix that are larger than 5 must move 1 position right. If so all the elements that are from the right of the 5th desired position definitely want to move right. So we will have to do that many operations. If there are many elements that are larger than 5, we have to move all the guys that were larger than 5 1 position right. Unfortunately, there is no free operation in the memory of the computer to do it, so it will be slow, but we will have to do it. And since we definitely have to do it, let's we understand that we will spend that much operations, so let's think about how we write the simplest code to move the 5 into its perfect position. And the answer is we can move the 5 by swapping. We will swap the 5, not only swapping, but swapping with the next element. So we consider the 5 and the previous element. If they are already in the correct order, the non-decreasing order, we just stop because the 5 came to its place. But if the order is bad, then we have to continue. And the continuation is just swapping these 2 elements and continuing moving the 5 from this position. So I don't know yet, like inside the program, I don't know if 5 is in the fitting position or there is more to be done. So after the swap, I continue checking where the swapping has to be continued. 5 is 5 smaller than 3. If it's equal or larger than wonderful places found, stop the iteration. But if it would be smaller, then I would swap them and continue the procedure. In this case, they are just in the good order, so I received the correctly sorted prefix of length 4. Then I try to, and what I do here, the correct English verb is insert, right? I insert the 5 into correct position. Then I insert a 6 into this position, and I think I use the correct comparison, so I compare them, and if they are equal, of course I don't swap them. It's both efficient not to swap them, and there is another smarter argument why you shouldn't swap them. It will be told quite soon. So do not swap them. 6 is wonderfully inserted. 9 is wonderfully inserted, and maybe let's also insert 1, because when you will if you will code this in programming language, there is a common mistake among novice programmers that this one will swap with a 9, swap with a 6, and so on. It will swap with a 2, and please make sure that your code doesn't try to swap a 1 with a degenerate index, with index -1. So definitely make sure that your code only swaps this element. So don't say the phrase swap this one to the left until it comes to the element that is larger than or equal to 1. Because in case of 1, there is no such element. You will swap and swap and swap, and this badly written for a while loop will also compare 1 with an existing element, and you will have an exception or something bad will happen. So please remember that you do the swapping either until you come to a good position and the next element is larger than, smaller than, equal than your element, or until you have swapped to the first 0th position, and that's also a reason to stop. Okay, so the one will be swapped, will stop over here, and in linear time, each element will be in at most linear time, each element will be inserted. So if the elements were larger and larger, the insertion will be actually quite fast. But if the elements were quite small or middle size, then the insertion would take linear times. And very quickly speaking, you can say the following phrase. So there are linear insertion procedures. Each insertion procedure takes linear time, and therefore the entire working time of the algorithm is linear times linear, which is quadratic. You can do it this quick, in such a short manner, but formally you can say that the first element is inserted by at most one swap, the first in the Python notation. So this is element number 0, you don't do anything about it. This is element number 1, you do at most one operation about it. For this element, at most 2 operations, swaps to it into the good place, and so on. For this place, element n-1 operations to at most to swap it into its good place. So once again, it's an arithmetic progression with size like n, sum n times n minus 1 over 2, which is really not important, because mathematically you will see that this formula grows quadratically with the growing of n. So plus or minus over here is not important. Anyway, it's a formally you write all the operation working times and receive the quadratic formula, or you simply say that there are linear number of swapping insertions. Each insertion takes linear number of swappings to the left. Good. So yet another algorithm with quadratic time, and this approach is, we already have everything perfect on some prefix. Let's extend this prefix of perfect situation a little bit. Like in real life, like you start with your own apartment where everything is wonderful, and then you like extend the part of the world in which everything is working fine a little bit more and more and more. Okay, so next sorting algorithm is quite known. It's called bubble sort. The name is a metaphor. I will show you the bubble over there. Actually, yeah, so let's start once again with some, the same data. There is a similarity between insertion sort and bubble sort, because that procedure of swapping and going, swapping neighboring elements and going in some directions is a good procedure. It does something good. But bubble sort does it from left to right, which is probably more usual for European language people. And okay, let's see. So let's do the same procedure, swapping looking at neighboring elements and swapping them well, for European language people, it's easier to do it left to right. So let's do it and see what happens. In this case, in bubble sort, first we do all the pairs from left to right. And what I mean, do the pair. I look at these two elements. If their order is already wonderful, I don't do anything. It's definitely stupid to swap these two guys, for example. But if their order is incorrect, I swap them. So 2 and 3 are not swapped, they are wonderful. 3 and 9 are not swapped, they are wonderful. 9 and 5 are swapped because the order is wrong. 9 and 6 are swapped because the order is wrong. 9 and 6 are swapped because the order is wrong. Oh, my example is too easy, but anyway. So what happens after such amount of working with pairs? Of course, it's just a stupid coincidence that my data is already sorted at this point, but what we can be sure about, for any initial array, what is definitely true? Well, consider the maximum element. Once again, well, it can be said that it's very similar to selection sort, but we'll see that some differences are present. So the maximum element, after we come to the maximum element with this pair procedure, we will take this and always swap it with the next and next and next elements. So by this procedure, the maximum element will finally come to this place, because once we start working with it, it will be swapped with the next one, swapped with the next one, and so on. So the maximum element will indeed come here. So if you do like an animation for this, a cartoon, if you draw a cartoon, then and say that they are bubbles and everything is located like this, so the huge bubble number 9, the large bubble will go up the water and float to the surface in the first part of the cartoon. So the first part of your cartoon will show the huge bubble 9 approach the surface, and that's this large 9 is called like a huge bubble. So the metaphor for the algorithm is bubble sort. Now, you cannot be sure in general what happens in the other part of the main prefix of the array. What you can be sure is that this position is wonderful, that 9 has the last position has the correct element. So if you don't want to remember anything or think about anything, what you can do is just repeat this procedure from left to right. If you simply repeat the full procedure, then what will happen? The next to maximum element in general case will definitely come to this position, so it will swap and swap and swap into this position, and this next to maximum element will be compared with the maximum element. Their order will be already correct, and you will not swap them. So the long procedure of the next for loop will also put the next to maximum element into its correct position. But as you can see, the last comparison is not needed. So if you don't want to think or remember anything, you can do all the comparisons, but you can also do the comparisons in a little bit more efficient amount. So you do all comparisons except the last one, from left to right. And now you can be sure that this element is selected. Well, it's almost like selection. In some way, it's like selection sort. So this element is selected correctly. And if you're inefficient, you can do one more long number of comparisons. But you can see that this last comparison on the next iteration is also not needed, because some next to maximum element will come to this position. you can compare it with the next to maximum element, but you will see that no swap is needed. So you don't have to do this comparison. And you can do less comparisons on the next level, then you do less comparisons on the previous of the next level, and just one comparison for this prefix. And once again, after this element is set correctly, we use the wonderful simple mathematical fact that the prefix of size 1 is already sorted, so you don't have to do anything more. So this is the number of swaps that the scheme of swaps that you do. And if you by the way, now we have the visual argument why the topic is quadratic sorting algorithms, because if the size of the array is n, we have to calculate the number of swaps in the bubble sort, and you see that this is an area of a for large n. This is almost exactly like a triangle. It's this figure is like strange, but it's almost exactly a triangle with side n. So the area of this triangle is n, approximately n squared, is n squared over 2. You can visually show that the number of swaps is the area of this rectangle is n about n squared over 2. So even visually we can show that the working time of this algorithm is n squared. Or you can formally sum up these numbers of number of swaps, of comparison, and receive the sum of an arithmetic progression, and once again receive this asymptotic formula. So this works in quadratic time, and we have yet another sorting algorithm. But let's finally get some fruits out of the fact that my example was really easy to sort. So the first long iteration, the first for loop, put 9 into correct position. And if you remember what happened, or you can rewind the video, the second iteration worked with these 5 numbers, and this comparison did not swap, this comparison did not swap, this didn't swap, and this did not swap. So the overall iteration over here didn't do any actual swaps. Think about it. If this was already a lazy iteration, like didn't swap, then your data didn't change during this for loop, and you are going to do the same comparisons, even subset of these comparisons with the same data. You already have checked that all the pairs are in correct order, with a space over there. So these comparisons will give you the same result. The data didn't change. You just do the same checks. Of course, they will tell you, okay, it's still the good order. So you will not do anything here. By the same reasoning, you will not do anything here. You will not do anything here. Okay, so the next long iterations, next for loops, will not do anything either. So therefore, if it happened, then you can break the entire loop. So in your programming languages, I hope that there is a break operator, the break phrase that you can use to break the outer for loop. So if some inner for loop didn't do any swaps, you break the outer for loop. You don't do the other iterations. It's exactly what the break operator does. And in order to check whether some comparisons were done, the usual way is just to store a single Boolean variable. You start with a Boolean variable with the value like false. So it means whether I have done any swaps. Wonderful name, like whether underscore I underscore have underscore done any swap. And this variable is initially false, and if you do actual swap in this position or in this position anywhere, you put true into this variable, and after the for loop, if it's true, then you do nothing, you just continue the usual work. But if it's false, then you know that the long iteration didn't change anything. The next long iterations will not change anything either, so you can break. and in some case the bubble sort will work even faster than quadratic times, but in bad cases it will work in quadratic time, which is normal for our topic today, for our lecture. Okay, there is also a next level understanding of bubble sort algorithm, because you can think about the example, the following example. So let us our array be the following. Let's start with a good example. So our array could be like 9 and then 1, 2, 3, 4, 5, 6, 7, 8. If you quickly think what bubble sort does on this data, so it swaps a 9 with 1 and so on, and the first left to right iteration will put a 9 into its wonderful position. The next left to right iteration will check that all the other guys are located in the perfect order, and we will stop the entire bubble sort. So on this array we swap a 9 into its wonderful position, we check second iteration that everything is good, and we stop in linear time. So we do n comparisons plus n minus 1 comparisons. It's about 2n operations, which is linear time. So on the array of such structure, the bubble sort works linearly. But consider another array, which is 2, 3, 4, and so on, 9, and then a 1. As an exercise, let's think what bubble sort does on this array. So the first long for loop will not do anything about 2, 3, not do anything about 3, 4, and so on. Will finally, and only in the end, it will swap a 9 and a 1. It will swap a 9 and a 1. So the long for loop, the linear for loop, did only one swap. Well, it actually put the maximum into its perfect position. It's a good thing. But so the bubble sort works. We did what we promised. We promised that this overall iteration does put the maximum into its wonderful position. It did, but it took, well, it didn't change the array much. So the next overall iteration will check 2 and 3, check 3 and 4, and so on, and only swap 8 and 1. So it will put an 8 into its wonderful position as it promised, but it will make not much changes, and so on. So each long iteration will just move one position more left, and we'll have to do all these iterations. So it will work the honest quadratic time. So interestingly, this almost sorted array takes linear time to bubble sort for bubble sort to work, and at this almost sorted array it takes quadratic time for bubble sort to work. But the natures of these two arrays were quite similar. We had almost the sorted array with one extreme value, the maximum or the minimum, moved to the wrong place. Here we moved the maximum to the bad position in the beginning. Here we put the minimum into the bad position in the end. So the structures, the natures of these arrays is more or less the same, symmetric. It's symmetrical to each other, but the working time is linear or quadratic. What's wrong? What is the mathematical non-symmetry of the bubble sort that makes two symmetrical mathematical situations so different? Linear time, quadratic time. Well, the mathematical non-symmetry that happened is the fact that we are like European language people, and we read from left to right. And so we decided voluntarily to do the first iteration from left to right. This is where we put the non-symmetry into the situation. We remember we read and write in natural language, and we said left to right is the important order for us. And this is the philosophical reason why the behavior is different. So working from left to right made it unfair for these two arrays. Well, maybe then we should do it right to left. But no, of course, if we do the same, just right to left, it's easy to understand that on this array we will work quadratic time, but on this array we will work linear time. So this will be wonderful, but this array will be processed quadratically in a very long time. So going on right to left always is also not an option. And here comes the interesting algorithm. So if we do all the long operations left to right, it will be bad here. If we do all the iterations right to left, it will be bad here. So it looks like we have to do both left to right iterations and right to left iterations. And we have to think of the way to use both of them, and the natural way is to alternate, to do left to right and right to left. And if you think about this left to right and right to left procedure, then, well, I'm trying to show the metaphor. It's how you shake cocktails, like, right? You do left to right, well, my hand goes left to right, right to left, and this procedure of my hand looks like what a barista does when he or she shakes cocktails. So this is called shaker sort, because the metaphor is this gesture of the hand. Well, we are European language people, so let's start with left to right. Well, we are used to it, so let's do the first iteration left to right, and I will erase this part. So, and let me erase the green part. So after the iteration left to right, we know that this position contains the wonderful element. The maximum is indeed put into this position. And now it's time to do my hand goes right to left in shaking the cocktail. So let's do it right to left. Do we need to do this comparison? No, this is already set perfectly, so there is no need to do this comparison. We do these comparisons, these four comparisons, right to left. And what do we receive by this position? What can we promise? The minimum element was somewhere in these 5 positions, and after the right to left swappings, we will take, at some point when we will find the minimum element, we will take it and drag it to the left by swapping and swapping and swapping. The minimum element will be swapped with this element, it will be here, it will be swapped with this element, and so on. It's you can, if you don't believe me, you can write down some examples and make sure that the smallest element will be definitely dragged, it's a good verb, dragged to this position. So we will have the minimum over here, and it's now time to go left to right in our shaking. So what comparisons are to be done? We don't need to do this comparison because the minimum element is already at its perfect position. So we shorten our set of comparisons by 1 position in the left. And we do this comparison, and this comparison left to right. Do we have to do this comparison? Of course no. This maximum element was already set a long time before in the perfect position, so it will be stupid to compare these 2 elements. So we do not extend the number of comparisons at each iteration anyway, and we remove from the set of comparisons that we do, we remove sometimes 1 comparison on the right, sometimes 1 comparison on the left. So they will be shorter and shorter and shorter. We will receive this element ideally set, and we will make these comparisons from right to left. We will have, after which we will have this element ideally set, and therefore we don't have to do this comparison because this element is ideally set. So we will start over here and do these comparisons left to right, and we will make this comparison ideally set. And then on the subarray of length 1, you don't have to do anything because if these all guys are placed perfectly, then by exclusion rule, like this is definitely also set correctly. So this is the idea of shaker sort. Not the idea, this is exactly the shaker sort. Once again, let me repeat the same approach, that if your iteration didn't swap anything, if some iteration didn't swap at any pair, then of course you did change the data, and the next number comparisons, which is a subset of these comparisons, will not find anything to swap either. So these guys will also not swap anything, and you can break once again. So you can once again introduce this Boolean variable. If some long iteration didn't swap any pair, then break the entire algorithm. Your work is already complete. You can do it once again in shaker sort, and we have this beautiful number of sets of comparisons. It's visually harder to understand that it's quadratic, but it actually is the same number of comparisons as before, just placed more interestingly. So it's if you sum up these numbers, the amount of comparisons, it's once again the sum of arithmetic progression, and the sum will be once again O large of n squared, the asymptotic amount of comparisons in the worst case is O of n squared. But in the wonderful case, think about shaker sort working here and here. For the for the upper array, we will put the 9 by the first iteration into its correct position, then go right to left, make sure that there is nothing to be changed, and finish in 2n operations. For the lower array, we will go right to left and put a one position to just make one swap. Then we will go right to left and put the 1 into its correct position, and then we'll go left to right and make sure that everything is correct. So we'll go there, and 3n operations. So in linear time, we will sort this array as well. 2n over here, 3 on n over here. It's linear time in both cases. So the shaker sort works wonderfully on the arrays that are already almost sorted, like sorted arrays with some distractions, with some bad changes, with a few changes, and it will work in quadratic time on any data set. So this is a next level of understanding of the bubble sort algorithm. Good. Okay. Now we will have to do the let's recall all the sorts that we have learned today, and check one of the properties that I definitely want to teach you during this lecture. So we have learned first it was selection sort, then it was insertion sort, then it was bubble sort, and then it was shaker sort. Let's now check the important property of well, I don't want to call it the topic, because you can think that it is yet another sorting algorithms. No, we just are learning the word stable. So some of the sorting algorithms are stable and some are not, and it is rather important for, well, you definitely want your built-in sorting algorithm in your programming language to be stable. I will tell you what it means and why you want it to be. So let's think about equal elements in the initial array. For example, I can make this 6 green and the other 6 black. So I mark the equal elements by something. In real life, it will be the other way. In real life, I think it will be, you will sort not the integers, but you will sort like students by some criterion. And so this will be a data structure, student with name, last name, first name, and so on, and like the average score 2. This is a student with last name, first name, and average score 3, and so on. So there are elements with equal average score, 6 and 6, but this has one last name, and this person has another last name. So let's think about several people with the same average score and different names. We are sorting according to the average score. So what happens to them? Before, in the original data set, the green person was to the left of the black person. So what is what is their final relative position? The sort is called stable if the relative position of equal elements stay the same. So a stable sort, it's not a sorting algorithm, it's the property of a sorting algorithm. Some sorting algorithms are stable. So it's stable if it leaves the same way the relative position, who is to the left and who is to the right, among the equal elements. Like there are several guys with average score 6. If the ones that were to the left initially are to the left in the end, then the sorting algorithm is stable. Let's recall the topics we learned today and check which ones are stable. So selection sort, we search in some other probably array, I don't know. We search for, let's do like this. Sorry, I need a longer example. So we search for the maximum, for the index of the maximum. We swap this guy with the last element. And when we do this swap, this 9 comes to wonderful position, but these 5s come to the position where 9 was stored. And consider a couple of 5s, all the 5s. There are several 5s in this data, but this 5 is now swapped down here, and its relative position with another 5 is lost. So their relative position change, and we will lose more and more of such information. So by this swap, we happen to be not stable. The selection sort in its normal implementation, well, it's in its usual implementation, is not stable. Unfortunately. So selection sort maybe is the easiest to code for somebody, but it's unstable. Now insertion sort. Well, there is, so there is the insertion procedure. This is, you have some already sorted left part, you have some already sorted prefix, and you insert the next element into the already sorted area in which everything is perfect. Well, you swap and swap and swap. No, I'm sorry, I will change my example one more time. So let's swap 6 into the already sorted area. So when you compare with the larger guys, you just swap them, and it's very normal. But as soon as you come to the area with the same equal elements, of course, I told you we don't make the swap of the 6 with its brother or sister 6. I told you that it's just inefficient and extra stupid operation to do. But the correct, better phrase, not better, but another phrase, is that also it would make it unstable. So their relative position some change for some reason that there is no smart reason for it to do. So once a 6 comes here, it doesn't interchange with the previous 6s, and the 6s that were to the left of these 6 initially will be still to the left of the 6 in the insertion sort. And the new 6s that are to the right will come to this region and will not be swapped, so they will stay to the right of these guys, which is exactly what we want. So insertion sort is indeed a stable sort. But we can extend this logic to bubble sort and shaker sort as well, because these three algorithms have the similar procedure. All we do is compare neighboring elements and swap them only if the order is bad. And you can prove this theorem if your sorting algorithm works only with neighboring pairs and never swaps the equal elements. And of course, if you implement bubble sort and shaker sort and compare elements and you see two equal ones, you don't do the swap. It's inefficient, it's extra work. Why do it? So you don't swap them. And in fact, any algorithm that works with neighboring pairs and doesn't do the stupid work of swapping the equal elements, all such algorithms will leave the order of the 6s. Oh, let me make the 6 red, in fact. Yeah. So the order of the 6s in any algorithm of such family will be preserved, because we just never swap 6s. So we can swap some different elements, but these 6s, yeah, any swapping of different elements doesn't change the relative order of 6s. And when two 6s are put into neighboring position, any algorithm of such family, even if compares this pair, the algorithm says, okay, they are equal, I don't change them. So such algorithm just cannot, by definition, change the relative position of the 6s. So all algorithms of this family will have the relative order of 6s the same, and therefore is stable. So all three of the four sorts we learned is stable. Now, let's understand why sorting algorithms should be stable. Maybe even better example is not programming built-in sorting algorithm in your programming language, but rather built-in sorting algorithm in a spreadsheet program. So you're using some spreadsheet program and you are sorting the data. Here's the thing. I'm very sure that all the major spreadsheet systems definitely have their sorting algorithms stable. And here's why. Consider many modern spreadsheet systems can support smart sorting. That is what I mean smart by the word smart. You can sort by the last name, but in case of the same last name, sort by the first name. It's very normal when you sort a lot of people. There are many people with common last name, like Smith or Müller or whatever in any European language. So many people with the same last name should be sorted by first people with the name Abraham and then people with the name Zoe in the end. How do you do it? In many spreadsheet systems, you can just sort by last name, and in case of equality of the last name, sort by the first name. But imagine that you use like very old school spreadsheet system that only supports sorting by one criterion. Here is the trick. First, you sort your people by the first name. It is very strange. You will have like a lot of Abrahams in the beginning, a lot of Zoes in the end, and it doesn't look like the sorting you need at all. Just people with first name A, people with first name B, and so on. Very strange. But if you apply to these data the guys and girls sorted by the first name, now you apply the sorting by the last name, we hope that the spreadsheet system has the built-in sorting algorithm being stable, and then you will have a lot of people with the last name Smith. But what will be the order of the people with the last name Smith in the end? So in terms of the current sorting by the last name, They are the sixes. They are the different elements with the same value by which we sort. They are all Smith and Smith and Smith. So the stable sort will promise the same relative order of Smith people. You will have Smith people preserved in the same order, and from the previous sort you knew that the order of people is by the first name. So Abraham Smith will come first, will be still first. So among all the Smith people, Abraham initially was very much on top, Zoe was very much in the bottom, and after the sorting by the last name, which is stable, all the Smith people came together, but they preserved their original order. So Abraham Smith goes first and Zoe Smith goes last. And you will receive the data sorted by last name, and in case of equality of the last name, by the first name. So you definitely want your spreadsheet system to allow this situation. So if you have data sorted by previous criterion, you do stable sort by another criterion, and the elements that have equal values will be still sorted by the previous criterion. So if you sort students by average score, it's quite normal to do the stable sort, and people with the same average score 6 would, in a good system, rather be stored by their last name. Why not? So if the original order was by last name and the stable sort was stable, then the guys with average score 6 will be A and B and C and so on, which is a good idea. All right. So 3 of 4 our sorts were stable, and it's a good part. And now we do indeed have the time for a bonus, one bonus algorithm. Like let's do the opposite. Let's do the shuffling of the array, because I really want you to see that you don't only learn specific algorithms, the specific 4 algorithms, but you also learn approaches. You learn the ways to work with data. So remember the insertion sort. Insertion sort is something I want you to recall. Like, it's just 40 minutes time, so you should recall it. What the approach was. You already have some prefix in which you are sure that the order is perfect. And what I mean, the order is perfect. You have solved the task that you were obliged to solve inside this area. And you want to extend this area by 1 unit, so that after your procedure, the order over here is perfect. The task is solved. Let's just do the same. But the previous task was to sort the data, and now the task is on the opposite, randomly shuffle. So if you make your own like casino or card game, playing cards, anything, board game, you want in your program to have a deck of cards shuffled. How do you do it in programming? Let's make this, because it will show you that you really want to learn not only specific algorithms but approaches of these algorithms. So I promise the task is having like, well, probably this was a deck of cards, like a 2 of hearts, a 3 of hearts, and so on, like an ace of spades, and so on. There was some data, for example, a set of cards, and after the end of your procedure, you want this deck to be ideally shuffled, and the formal mathematical notation would be that all the permutations of the data should be equally probable. The probability of any order of these elements should be the same. If you are good in math, then for n elements, you want every order to have the probability 1 over n factorial. Let's leave it as an exercise. Make sure, it's good to understand that any order of the original array should have probability 1 over n factorial. Let's do it. Funny, it will sound funny, but we can be sure that on the area of size 1, once again, we have the problem solved. Indeed, all the orders of this one element have the probability 1 over 1 factorial, which is 1. Well, let's think about it. This is the best way. Well, if your task was to shuffle the deck of size 1, then you are done. You couldn't do better. That's it. So we start with the area of size 1, and now let's go to some larger area. So we have already solved this part. We proved to ourselves that all the permutations of these guys are equally probable. Basically, these 5 elements are perfectly shuffled. Let's make this task solved on this area. Let's make the first 6 elements perfectly shuffled. Well, this card, like 2, 3, 4, 5, 6 of hearts, so this is probably 6 of hearts, and it should go somewhere inside this prefix. But where should it go? Well, it should go here, or here, or here, or here, or here, with probability 1 over 6. So if it's in, we are working with 6th card in usual, non-programmer notation, so it's 5th card in Python enumeration, but it's 6th card in usual people enumeration. So when we are working with 6th card, the probability of it going into each of the positions should be 1/6. It's not hard math. Of course, among all the possible permutation, 1/6 of the permutation have 6 of hearts in this position, 1/6 in this position, and so on. Note that it is normal for 6 of hearts to stay in this position. It's possible that in some permutations the cards are left over in their initial positions. Why not? It's also a possibility. So this data was already shuffled. The new 6 of hearts should 6 of hearts. I have red marker. Should go to some of the 6 positions. And how do we do it? By a simple swap. We select this index randomly and we swap the new card with the card on this position. Probably it's the same position, and that's it. We select the position with the probability 1/6. We do the swap, and it can be shown that now all the permutations of these 6 cards are equally probable. Please make sure that your code does allow the swapping to the same position, because otherwise the ace of spades, think about it, if spades, if you forget about allowing this swap, then your casino will have the final ace of spades moved definitely to one of the 51 positions over here. It's interesting, if you do this bug, then the users of your casino will know for sure that ace of spades is moved somewhere down here, and they can like bet on the fact that the last card is not ace of spades for sure. That's not how a good shuffling should be. So yeah, there are other problems as well, but for example, the users will know that ace of spades is not here. Why give them such information? That's mathematically incorrect. So please don't make this bug. Then each new card should be put into any position among the previous position and the same position with equal probability. You just select the position, make one swap, and in swaps you just swap in this card into already shuffled array, then you swap in this card into already shuffled array, so there will be n-1 swaps, and it's linear time. No one cares about -1. In linear time you will shuffle the original data structure, the original elements, such that all the permutations are equally probable. And the approach is the same. Have the problem solved here, extend, and extend. So please, when you learn algorithms, not only learn the specific code by heart, but also try to take the approach, the idea of the algorithm to your brains so that it can be reused. And I think it's a good example. Okay, thank you for your attention. Have a nice day.